Lecture 5, Climate and Climate Change. We're talking about climate change in this unit under climate because climate is never static. It is in constant change. And to understand climate, you have to understand that it is not a one and done. It's always been this way. It's always going to be this way. What I do want to make very clear is we're not talking about climate change in the recent sense. We're talking about long-term geologic scale climate change that happens over hundreds to thousands to millions of years, and that there is a cycle of warming and cooling and wetting and drying that happen. So we're going to stay in that lane for this class. So hopefully it's some new material for you. I know that you've had an education of more recent climate changes under human-induced change, mostly through your K-12 education, but we're going to go back and build you a foundation on natural climate change in this lecture. So with that, because we're going to be talking about climate change, and climate change is hotly debated, it's a good place to talk about science and how science and the science of climate change and climate in general is the same understanding that all other sciences take, whether it's nuclear medicine or computer science and modeling, whether it is science of quantum physics or biology. All science has to undertake the same methodology, which is about rigorous testing. And it's testing to get to better understanding and better answers. I'm going to repeat myself here, but it's not for proving. Science does not set out to prove anything. They're setting out to understand something and improve the understanding. And it has the flexibility to make corrections when our body of understanding improves. Oh, we thought we understood it this way, but it really happens a different way. And that usually comes because science and the questions that it takes a long time to move the bar forward, because it has that rigorous testing that a lot of people take the time to push at. The other thing that we have in terms of getting better bodies of knowledge are our technologies, and when technologies improve, our ability to ask and answer questions improves, and it usually increases the rate of getting information back. So it might seem a little bit quick that scientists sometimes say, we believe this is what's happening. That belief is always couched or phrased that way rather than an absolute, because a good scientist knows that in the future someday that a body of knowledge will come about that either improves what we understand, it holds it in solid, and we've had a lot of that, it just doesn't make the news, or it has changed our understanding and it's turned a narrative around a little bit. So I've got the example of that lovely computer here that had the punch cards back in the 60s and 70s, and how far we've been able to improve our climate science and all of our other sciences because technology has improved. So when you have more people working on something, more brains are engaged, we're going to get there faster, we're going to have better question asked, we're going to have more people pushing at the science to make it better, to get rid of the things that aren't working and move towards the things that are working. And back when this individual was the technician and she was feeding the punch cards, there were probably a lot of scientists all dependent upon this one very large machine. By the time we moved into the 1970s, people were starting to get their own personal computers, and they could all work independent of her, and they could work a little bit faster. And of course, as computers became better themselves, more people could work better, faster, and push against the science and make corrections quicker, and work towards a better understanding. So a lot of what we understand today is because things have not been refuted. Everybody working on asking questions and answering questions only knows that the science gets better when we push against it, when we're not in conferring, that we're not in a relationship where, oh yeah, I'm going to agree with you. Agreement is not the name of the game. Asking the better question and getting the better result is the name of the game. So this is nobody ever gets a free pass. It's always challenging outcomes, always critiquing the outcomes to move the science forward. And it's never a done deal, and it's never perfect. We aim towards perfection. The process is accurate, but we know that the result is always a moving target, and that's what I mean by perfect. All right, so you know some things. You were great scientists when you were little kids. You went through a process of observing and testing phenomena and asking really good questions. So the question I want to put to you today in terms of what you know is just to do a little reflection. I want you to think about the last 20 years or so of your life. And if you're younger than 20 years, go back 18, 17 years and think about some of the things that you know in terms of climate. And climate, as you should remember from a couple of units ago, is 30 or more year averages of weather conditions. So we're going to take 30 years of average snowfall in February and see if this 30 years changed from the last 30 years, from the last 30 years. That's going to tell us that things are changing, that there are no strange anomalies here. We're accounting for the unusual events when we take averages. So as you're looking at the last 20 years, and you're wanting to know whether there's some changes happening or if things are static and staying the same, you might ask yourself, when was the first time that the snow would first really fall? Do I remember? Was it in November or December? Did we get snowfalls in October? When was the last time that snow melted out? What did the snow look like in December and January? Is it different than the snow that falls in March? When it fell, did it stick and hold in place, or did it melt in between? Some of the things that I've observed over the last 19 years in Northeast Ohio was when I first arrived, it would snow and the snow would stay on the ground through to March. Over the last several years, starting about 15, 16 years ago, snow would melt out quite regularly. And the data proves to us that we've actually broken snowfall records. We have had more snowfall in several years than we had in the 1980s, in the 1970s, in the 1960s. But our grandparents would probably say, what are you talking about? I don't see any snow on the ground. Well, the difference is the snow melted and we didn't see how much total volume accumulated because it didn't snow and then a new volume fell on top of that old snow and then a new volume fell on the previous snowfall and it just started to pile up. There was no piling up because we were melting that snow out. So that tells us a couple of things. It's warm enough for it to snow. You can't have snow unless you heat the atmosphere so it evaporates. And it happens to be warm enough that things are melting in between. So something's happening, right? What's happening? Is it natural? Is it something else? Those are questions for the scientists to ask and to test, right? So we could ask those questions about different seasons. We could ask about hurricanes, or we could ask about summer thunderstorms. We could ask about sunny days. How many sunny days are there in Northeast Ohio over the course of a year, over the course of the last 30 years? Has it been the same, or is it changing over time? So that's the kind of thing that you can observe for yourself. I have an example of the type of question that one might ask, and I've chosen sort of, I hope, a benign question in asking, is the sky blue? We might all look at the sky today and say, yep, the sky's blue, but a lot of scientists have asked, is the blue that I see the same blue as what someone else sees? And people could argue, no, the sky is not blue. What you say is blue is my purple or something else, right? So we need something better to measure blue by, and what we can measure is the wavelengths from the electromagnetic spectrum. And in the electromagnetic spectrum, the range of wavelengths that make up all the different hues of blue range from 450 nms to 495 nms. So if I wanted to know, was the sky blue in Youngstown, Ohio on May 25th, 2025, I'm going to go out at different places across Youngstown, Ohio at different times of the day, and I'm going to take that measurement. I'm going to come back. I'm going to take all of the wavelength data that I have acquired, and I'm going to average it out for the period of time from sunrise to sunset. And if that number falls between 450 and 485, indeed the sky was blue in Youngstown, Ohio on that given day. So let's say the number came out as 461. It was a nice blue day in Youngstown, Ohio. If I want to know whether it's we have blue skies in Youngstown, Ohio every day of the year, I'm going to go out, I'm going to measure every day across the day for one full year, and I will tally up all of the days that have a wavelength between 450 and 495, and I'll tally up all the days that have a wavelength that is outside of 450 and 495, and then I can answer that question. No, we don't have every day of the year with blue skies, or yes, we do. And in which case, then I can ask the question, why we do or why we don't. So again, science is not set out to prove something. It does not want to prove the sky is blue. It does not want to prove that cancer is the product of some particular condition. When we try to prove something is the result of something else, then we have a high likelihood of getting it wrong, that there are several other reasons out there that could be the result of a blue sky or a particular type of cancer. And if we don't get it right, we can do a lot of harm. So science is about asking the question. So even when we find out that the sky is blue, we could then ask the question, well, what is the range of blue in Youngstown, Ohio? Or why do some people not see blue? And then we can follow that line of questioning. So with that, I've got 3 sources here that if you're curious, you can explore. They're all from the University of Berkeley, that talks about the misconceptions of what people understand science to be and not to be. So I encourage you to have a look at that. With what science is and what science is not is a hypothesis testing. We're testing a hypothesis, and hypotheses are a binary set of questions that are asked in 2 very clear ways that are going to have a yes or no result. It's definitive. So I've got an example here in terms of hurricane and strength. So the question asks for the what we call the null hypothesis, that's HO, is that hurricanes are getting stronger because ice melting is creating a lower albedo. Now you'll remember from albedo that a high albedo means high reflection. It's usually light colors like snow or white fluffy clouds, and a low albedo or lower is going to be dark surfaces. So certainly when ice is melting, the volume of ice is going to be reduced, which means it's going to be lower albedo. So the question asks, are we getting stronger storms because ice is creating a lower albedo? We're going to take the data, we're going to sample that data, and then we're going to test it, and then the answer is going to be yes or no. Simple. And in that testing, we have the alternate hypothesis, which is that the hurricanes are not getting stronger because more ice is melting and creating a lower albedo. I want you to notice that the question is the same. We've just added a not. We've not changed the question in any way other than to make it a negative. So if I agree to the hypothesis, the null hypothesis, then my alternate hypothesis has to be a no. If I disagree with my hypothesis, my null hypothesis, then my alternate has to be a yes. If I get anything different, then I've asked the question wrong. It has to be lock in step. It has to be definitive. Once I have a definitive answer, then I can ask a subsequent question that comes out of, but why? Why did I get a yes or why did I get a no? So climate and the answers that we have today regarding climate come out of those yes-no hypothesis testing. So when we talk about climate variability, what we're looking at is the climate for somewhere like Youngstown, Ohio, is different than the climate that we're going to get in Phoenix, Arizona, which is different than the climate that we have in Paris, France, or in Colombia or Beijing, right? Very different geographic areas have very different locational characteristics that are going to have distinct climates. And over time, the climate at Youngstown and the climate in Beijing and the climate in Colombia have changed over time because there are external characteristics to the earth that make those changes happen. We can map out climate regions. You and I can drive from Youngstown to Cleveland and think, oh, this is within the same climate sphere. There's not a lot of difference. Maybe in Cleveland there's a little bit more moisture. If I drive to Pittsburgh, we're going to say the climate is pretty standard, pretty similar to Youngstown. It might be a little bit cooler because it's higher in elevation. But for the most part, a zone which is delineated as a particular climate is the average climate conditions for every day of the year that are statistically similar between their nearest neighbors. So Cleveland, Youngstown, and Pittsburgh are in a climate zone. We're in a different climate zone than West Virginia or Western Kentucky or Western Tennessee. I think we can all agree that the climates there are different than they are in Northern Ohio, Western Pennsylvania. So those statistical average across all those communities are going to be different. Likewise, if we go to Texas and Arizona, those climates are more similar than they are to our climates here. So those are the geographic implications. As the climate changes over time, we're going to see that some places are going to expand and shift and other places are going to retract. So when the planet gets cooler, we're going to see places like Texas really shrink. Those warm areas are going to get smaller and smaller, and they're going to move south. When the Earth's climate warms, then we're going to get an expansion of warm environments, and then the cool places are going to shrink up. So it's a seesaw effect that goes back and forth. Again, I want to remind everybody that we're not talking about recent climate changes over the last 200 or more years. We're just looking at the long-term climate.